test next week, but I just want to continue my lecture for chapter 9. My chapter 9.1 is sequence. This section we have chapter 9 we have 10 sections, so I'm thinking about I'm gonna have the next test 9.1 to 9.6 only. All right, I'll send you an email for the homework later. All right, so let's look at some example here. Oh, before that, make sure that you read the theorem 1.9 to 9.1 to 9.5. It's very simple and you can just read it, right? So let's look at example here. We're gonna simplify the factorial. Let me review you factorial a little bit. If you have n factorial, what it means is that it means n times n minus 1 times n minus 2 times all the way to 2 to 1. In the calculator, you can use the calculator button for n factorial. Now the special one is 0 factorial. 0 factorial is always equal to 1. Now from this example, I don't have a number, I have a variable, so we cannot use calculator. So let's look at the first one. Right, the first example, I have n plus 1 factorial over n factorial. The numerator is bigger, so I'm going to rewrite the numerator. So I can write it as n plus 1. Alright, the next step lower would be n, and I'm going to stop at n factorial. The reason is that because I have n factorial on the denominator, so I can cancel this. So I'm going to stop at n factorial. That way I can cancel this too. Alright, so the answer will be n plus 1. Let's look at the second one. The second one, I have n factorial on the numerator, n plus 2 factorial on the denominator, and denominator is bigger than the numerator, so I'm going to rewrite the denominator. So numerator, I keep it n factorial. Denominator, I will write it as n plus 2. The next one will be n plus 1, and then n factorial. I'm going to stop at n factorial because I can reduce the n factorial here. So my answer will be 1 over n plus 2 times n plus 1. Alright. The third example, the numerator is bigger because I have 2n plus 2. The denominator, I just have 2n. So I'm going to rewrite the numerator and find a way to reduce this. So I'm going to write it as 2n plus 2. Okay, the next one will be 2n plus 1. The next one will be 2n. And I'm going to stop here because I have 2n factorial on the denominator. So I can reduce the 2n. So my answer would be 2n plus 2, 2n plus 1. Alright? You can leave your answer this way. You don't have to multiply it out. Alright? Let's look at the next type of question. Find the limit, if possible, of the sequence and determine the converges or diverges. Again, converges is mean it converges to one number. It can be positive, could be 0, can be negative. Diverges is mean it go to infinity or negative infinity. So what I'm going to do is I'm going to take limit first. Alright, I'm going to take a limit as n go to infinity, alright, of this sequence, which is 6 plus 2 over n squared. Alright, that is a theorem that you have two terms. You can take limit on each individual term. So I'm going to have limit as n go to infinity of 6 plus limit as n go to infinity 2 over n squared. The limit as n go to infinity of 6, you're just going to have 6. limit as n go to infinity. As n go to infinity, this second term will be 0. So 6 plus 0 is 6, is a number, so it converges. Alright, now let's look at the next one. I have a trig function, same thing, I'm going to take a limit of this sequence. So it's going to be limit as n go to infinity. I have cosine of 2 over n. Right? As n go to infinity, this 2 over infinity will be 0. So you're going to have cosine of 0, which is 1, and that is converges. Let's look at the next example. The next example, I have a polynomial on the numerator and denominator. Again, I will need to take a limit, but I have the highest degree is n squared here. So I'm going to divide every term by n squared, right? So I'm going to have a limit as n go to infinity, 10n squared over n squared. I'm going to divide every term by n squared, plus 3n over n squared plus 7 over n squared over 2n squared over n squared minus 6 over n squared. Next step I'm going to do, I'm going to simplify this before I take the limit. So the first term here, the n squared and the n squared cancel. I have 10 plus 3 over n plus 7 over n squared. That's my numerator. My denominator, I left with 2 minus 6 over n squared. Now I can take n go to infinity. So this term will be 0, 0, 0. I end up with 10 over 2, which is 5, which is converges. Alright, let's look at next example. Let's look at another example. Oh, before that, I just want to mention this theorem is 9.1. It's called limit of a sequence. I summarize it a little bit, alright? So the theorem said let L be any real number. So L is a real number, and you have a limit as x go to infinity, f of x equal to L. So f of x is a function here, and the limit of this function is equal to L, which is a real number. And if you have a function is equal to a sequence, a sub n here is a sequence, then the limit of a sequence as n go to infinity is also equal to L. Alright, that's what the theorem says. So we're going to apply this theorem for in the next example. Now this example, they want you to find the limit of this sequence. So what I'm going to do, I'm going to rewrite a function f of x, which is the same as the sequence. You see it's exactly identical. And then I take a limit of this function as x go to infinity. Then as you can see, as x go to infinity, I have infinity over infinity. So I'm going to apply the L'Hospital rule. Alright, take derivative of numerator, I will have 2x. Take derivative of denominator, I have 2 terms. The second term is just going to go to 0. However, the first term, I'm going to use this formula. Alright, a is a number, u is a variable, so it's going to be a to the u is ln a to the u, and u plum. So I'm going to have ln, my a is 2 to the x, derivative of x is just 1. Right? Again, if you apply limit as x go to infinity, I have infinity over infinity again. So I'm going to apply L'Hospital rule, and on the numerator, I'm going to have 2x, I'm going to have 2 for the derivative. On the denominator, I'm going to apply the product rule. So the product rule, I'm going to have the first term times derivative of the second. Again, this is the second term. Derivative of this It's just this whole thing which we just did. Alright, plus second time derivative of the first. There's two ways you can think about this. Derivative of the first, this is constant, it can be 0, or you can apply this definition here. My u is 2, so derivative of 2 is 0. However you want to think about it is again, is a constant. After that, I simplify a little bit. I have two terms of this, so it's ln2 quantity square 2 to the x. As x go to infinity, this whole thing is 0. And I apply theorem 9.1 because of the function. The function that I create here is the same as the sequence. One go to 0, then the sequence also go to 0, which is converges. Alright, last two example. I just want to show this example to you. Alright, write an expression for the nth term of the sequence. I have this sequence. I want to find the general term of this sequence. So on the numerator, I have 1 everywhere. So I'm gonna assume it's gonna all be 1. So I have 1 here, 1 here, 1 everywhere. On the denominator, I have 1 over 1. 2, I rewrite it as 1 times 2. 6, I rewrite it as 1 times 2 times 3. 24, I rewrite it as 1 times 2 times 3 times 4. And then 120 is 1 times 2 times 3 times 4 times 5. You can guess that the next one going to be 1 over 1 times 2 times 3 times 4 times 5 and times 6. So the general term of this sequence will be 1 over n squared because 1 over n factorial because the denominator is n factorial. Look at the next example. I have 2, 4, 8, 6, 32. I rewrite it as 2 to the first, 2 to the second, 2 to the third, 2 to the fourth, 2 to the fifth. I would expect the next one will be 2 to the sixth for the numerator. For the denominator, I have 1, 3, 5, 7, 9. That's the odd number. It's all odd number. So my denominator would be 2n, which is an even, minus 1 is make it odd. And some of you might have different a sub n, alright? But make sure that you check and it's correct. Alright, we finished 9.1. Have a good day.